Hello and welcome to the third and final part of the theory for Pythagoras' Theorem Year 9 edition. So today we're going to be looking at an extension of sorts in which we look at the examples of three-dimensional shapes and finding the diagonals of these shapes using Pythagoras. So let's get straight to it. So first, let's just take a step back and think about what we've done with Pythagoras so far. We've looked at 2D triangles and we've looked at how to find the hypotenuse and other sides given two of the three sides. So if we know that this is 5 and we know this is, let's say 6, then we know that this is just going to be the square root of 5 squared plus 6 squared. And that is your usual Pythagoras' theorem. Then we were able to take it a level further and say, well, what if we have this rectangle and we want to find the diagonal of that rectangle? Well, in that case, we can see a right angle triangle exists. And let's say the side of the rectangle is 5 and 12. Then we're able to find the length of the diagonal by using Pythagorean triads, which was in one of our previous videos. And we know that 5, 12, and 13 is going to be a Pythagorean triad. So we can say that the diagonal is 13. Now, in 3 dimensions, we're going to be using the same exact principles. We're going to be finding right angle triangles and applying Pythagoras' theorem, but this time we're going to be doing it more than once. So let's have a go at this particular question to give us an idea of how to use Pythagoras in 3-dimensional scenarios. Given a cube with side length 2, find the length of its diagonal. So first, as always, it's a really good idea to draw a diagram. So let's draw what our cube is going to look like. So I'm not an artist, but I think this does a fairly good job of representing what a cube would look like. I'm just going to use dotted lines here to indicate bits we can't see from front on. And you can see that we have a cube and the side lengths, every side of a cube is the exact same. I'm just going to let that be 2. So we need to find the diagonal of this cube. And what that means, I'm going to use a different color here. This, for example, would be a diagonal of the cube. Now, the question is kind of poorly written in terms of this is technically also a diagonal. You can see like on this front face, this red could be a diagonal. But what we actually are trying to find is this orange line. So the diagonal from 2 opposite corners of our cube. So how do we go about finding out this length? Well, we need to split this up into a right angle triangle. And hopefully you can see that we can construct a right angle triangle using the floor of the base of our cube. And you can see there's a right angle triangle just like this. So I'm going to draw out that right angle triangle over here. So let's see, we know that this side here is the same as this side here. We know that this is going to be 2 units because it's just the side of our cube. This is what we're trying to find. So I'm going to let this be x. And do we know what this is? Well, you might be tempted to say it's 2, but if you just think about it, this side is 2, this side is 2. The diagonal of our base would definitely be more than 2. So this is where we're going to be using Pythagoras again. So this time I'm going to draw a new triangle. Hopefully you can see on the base here, we've got our diagonal of the base. We can see we've got this here. And if I just draw it like this, hopefully you can see it's a right angle. In fact, if we look at it from a bird's eye view, you can hopefully see, I'll draw this whole cube from a bird's eye view. So just pretend this is the floor. We're trying to find this particular distance here. So how do we find that? Well, we can draw this right angle triangle. We know this is a right angle. We know that this side is the same as this side. So that's going to be 2. And this side here would be corresponding to this side here. And that's also going to be 2. So let's call this y. And so if this is y, then this would also be y because these sides are the exact same and they're just part of 2 different triangles. So how do we find y? Let's do that first. Using our basic Pythagoras, we can say that y squared, that's the hypotenuse squared, is equal to 2 squared plus 2 squared. Those are my short side squared with my other short side squared. So that means y squared is going to be 4 plus 4. And so that gives us y squared is equal to 8. And so we can say that y is equal to root 8. So that's what y is. So now I can replace this y in my other diagram, and I can say that this is going to be root 8. So now, how do I find x? Well, to find x, I would say that x squared, writing my Pythagorean statement again, x squared is equal to my first short side squared, so 2 squared, plus my other short side squared, so root 8 squared. Now, we know that x squared is just going to stay like that for now. 2 squared is 4. Now, whenever we square a square root, it basically just cancels out because they're opposite functions. And so we can say that square root of 8 squared is going to give us 8. So we can say that x squared is going to be equal to 12. And so we can say x is equal to the square root of 12. So to find the diagonal of this cube, we use Pythagoras twice in 2 different triangles. But the key is that one of the sides that we found out from the first Pythagoras was also the side in our second triangle where we use Pythagoras. So let's move on to a bit more of a general case and have a look at it from there. So here we've got not a cube, but a prism, and we want to find an expression for the length of the diagonal in terms of L, W, and H. Now, this is a bit more tricky, but I do want you to have a go before I go through the solution. Make sure you're trying to find an expression for this blue line over here. So pause the video and have a go. And now let's go through it. Okay, so what we want to do here is create 2 right-angled triangles to solve for the blue line. So the first one I'm going to do is making this the hypotenuse. So I'm going to draw a triangle that runs straight through here. So this here would be my right angle triangle. So I'm going to draw this triangle over here so that it looks nice and easy here. So remember, this is the side we're trying to figure out. You can see that this side here corresponds to this side here. So I'm going to call that X. Now, well, what do we know about this triangle? Well, we know that this triangle here, this side over here is the same as H, right? Because it's just the height of our prism. And that corresponds to this side over here. So we can say that that is H. Now, this long side here corresponds to this diagonal of the base. Now, we do not know what the diagonal of the base is. So we might want to construct another triangle to figure it out. So I'm going to draw a triangle that looks like this green triangle. And you can see that this green triangle is a right angle triangle because this is a prism, which means it's a rectangular prism, which means that this is a 90-degree angle. Now, let's just draw this triangle over here. So I'm just drawing this triangle over here now. What do I know about the sides? Well, I know that this is the side we want to find out. So I'm going to call this Y because this side here corresponds to this side here, which also corresponds to this side here. Okay. I know that this side is the width. So I'm going to call that W. Now, I want to call this side L because we'll call it L here because that is the length. Okay, so L would be the same as this side, same as this side, same as this side. So now it is a bit daunting, but to use Pythagoras theorem on this triangle, we just use the same expression. So we say that the hypotenuse squared is equal to the first short side squared, so W squared, plus second short side squared, which is L squared. So now we have y is equal to w squared plus L squared. We don't know what that is, but it's okay. We know that y is just going to be the square root of whatever that is. So now that we've found out that y is equal to w squared plus L squared, the square root of that, we can chuck that into here. So we can say that this is square root of w squared plus L squared. Make sure the square root covers everything. Now, we write an expression for this blue triangle. So we can say that the hypotenuse squared for this triangle, so x squared, is equal to the first short side squared, so h squared, plus the second short side squared. Now that means it would be the square root of w squared plus L squared, and we're squaring that. Now, as I mentioned in the previous slide, whenever we square root something and we're squaring it again, we're just undoing the square root basically. So we're going to say that it's h squared plus just whatever that is, w squared plus L squared. So we come to the equation x squared is equal to h squared plus w squared plus L squared. Now it's getting a bit messy, so I just might move it over here. So we just have x squared equal to h squared plus w squared plus L squared. So how do I find x? Well, to make x the subject, I just square root it. So I'm going to say x is the square root of h squared plus w squared plus L squared. And that is an expression for the diagonal in terms of h, w, and L. So this would be our final answer. So hopefully that's been a really good introduction for how to attempt 3D Pythagoras problems. In our next video, we'll be covering a few more concrete examples with actual numbers. So yeah, we'll see you there.